Hi, I'm Nathan Mikulski. I'm going to take you through a quick review of topic 1, which is energy methods. Alright, now our objective with this unit was to calculate deflections based off Castigliano's theorem. And we use Castigliano's theorem as a simpler way to analyze deflections instead of having to go through multiple derivatives of force and position and like that. So, what is Castigliano's theorem? Castigliano's theorem is when forces act on a Castigliano's theorem says when forces act on an elastic system subject to small displacements, the displacement corresponding to force in the direction of the force is equal to the partial derivative of the total strain energy with respect to that force. Now, what does that mean? What does that kind of look like? It looks like this. It means that your deflection is equal to the partial derivative of the total strain energy, which is represented by U, with respect to the force applied to it. Now, what does that really look like? Let's go through a quick example on that. So here we have a beam of length L and with properties E and A. Now, when a force F is applied here at the end of the beam at point A. Now, we're asked to find the deflection of the point at A. So first, we must find the total strain energy of this force, right? So we define strain energy as the integral of m squared over 2EI, m being the moment and E and I being material properties. And then that is with respect to x. Now here, for this problem, the moment is equal to the force times the distance and we're measuring the distance here from the left. Now the partial derivative of m with respect to f, or this moment with respect to this force f, is going to be negative x, and that's simply just taking the partial derivative of your moment. Now, our deflection equation, it looks something like this, which is just going to, let's go through this again as like a different thing, right? So this is going to be the partial of this strain energy, so this partial of this part right here, with respect to the partial of that. So let's work through it a little bit more. This derivative right here, deflection, is equal to this. This is just a little bit more of the rearrangement, but this is still basically this equation, just rewritten. So this is going to be equal to the integral of the moment over EI times the partial derivative of the moment with respect to the force. Now, let's rewrite that and plug everything in here. So our m, remember, was negative f of x, and our moment with respect to the force was negative x. Now, through calculus and all this other stuff, we get to this point here where our final answer is 1 over 3EI times FL cubed. Now, what does that mean? It means that the deflection at this point is based off of the force and the length and these material properties. And we found this out by using energy methods. If we would have used typical means like we've learned in, say, classes like dynamics and others like that, we'd have had to go through several more iterations of derivatives and second derivatives just to get our answers, and then we'd have to go search and find constants as well. So this is kind of going to prove that Castigliano's theorem, or energy methods, is a faster and sometimes more efficient way to find deflection in beams. Now, I mentioned earlier strain energy. Strain energy is critical to the energy methods. And strain energy, strain energy is deformation, or where work is done, and strain energy is the energy stored from deformation. So as a beam deflects and more energy switches to potential energy versus kinetic, meaning more energy switches from actually moving the object to more energy resisting that motion and trying to push it back something else, that stored energy is going to become strain energy, which is somewhat a form of potential energy. Now, we're going to define strain energy here as just kind of a general problem is delta W, or strain energy per unit volume, as 1/2 times sigma, which is stress, times epsilon, which is strain. And then to get our just normal strain energy, we're going to switch to the integral, or we're going to integrate that over the volume, right? Now, to do this, we're going to have multiple different multiple different types, right? One would be axial, one would be bending. Now let's look at axial first. Axial strain energy is strain energy that comes from tension and compression, or the stretching and squishing of things. As kind of shown here in this basic picture, in this case just happens to be tension. Now, let's define our deformation in terms of other things. Our deformation is going to be the change in length over the length. The delta L is going to be the FL over EA, which is one of the equations you learned in mechanics of materials. Delta, or your sigma, which is going to be your stress, is going to be force over area, and your epsilon is going to be force over E times A. All right? Now let's plug all these in back into this original delta W equation. What do we get? We get 1/2 times F over A times F over EA times A dx. Now what does that reduce to? I know this is kind of a change of variables, but bear with me. It's going to boil down to U is the integral of F squared over 2EA dx, right? Now, that's for tension and compression, but we're going to be more interested in, especially in the cases shown above, and as you can kind of look down here earlier, we'll get to those, is going to be more on the bending side of strain energy, right? So we're going to redefine sigma x as negative mx over I, and epsilon x as sigma x over E. Now when we plug those back into this equation, which is rewritten from here and here, we get 1/2 sigma x epsilon x dx, or dv. Now when we plug in both of these and work out the math, it'll boil down to U is the integral of m squared over 2EI dx. This becomes important because this is the strain energy equation that we know, and which we design up here that we didn't really quite talk about yet. This is going to be the strain energy equation that we're going to use for a majority of this rest of it, and so it's very important that we know this one and understand where it comes from. Now, like shown here, there's many different ways to apply it, and there's many different situations like this one. You could have this one where it's one force over with 1 point, and you want to find the deflection at that point. You could do it where you have multiple forces over the same area, and you do want to do it that way too. So you just have to apply these different equations, you'd have to apply these two equations and work out for the multiple locations. But what if, per se, we have a situation like this, where we have a force applied at one end, and we want to know the deformation at this middle point, for example, or a point that's not directly at where the force is applied. Well, how do we do that? We may try to approach it the same way we approach this, or in other ways, but we run into one problem. The problem is we have too many variables and not enough equations, too many equations and not enough variables to put in them. So we have leftover information that we can't solve for. How do we get around that? We have to use a fictitious force. A fictitious force, what's that, you ask? Well, a fictitious force is going to be a force with 0 magnitude that we're going to apply at the point we're interested in, and we're going to use that as a placeholder almost to help fill out our equations and make the problem solvable. Give me 1 second. So, how are we going to do this? Well, first let's apply our fictitious force here at point B. Let's give it magnitude Q. Okay? So, we want to know what this is. So let's first draw free body diagrams and try to find the moments. So let's start by analyzing this problem from the right-hand side. So what we're going to do is we're going to make a cut here. We're going to try to analyze it like a normal making that problem and a deflection problem. So let's make a cut and try to solve a moment about this side, right? So we're going to apply our moment around the cut with our force, and we have our direction. So the sum of moments around this direction in the negative direction is going to be this m plus p times the distance to this cut. We're going to set that equal to 0 since it's not moving. Now let's rearrange this to have m equals negative px. All right, cool. We have our moment equation for this first side. Now let's keep that in mind and move on to this next side. I'd like to extend this to where we have our cut on this side of the fictitious force, right? So we're going to sum the moments again, kind of in a similar process where we'll have an m here, q, and p this time. So what are we going to do? We're going to have our m, our sum of moments is going to equal m plus the q, this force here, times x. This time our x is going to be this distance from this force here. That's going to be our x. Ooh, sorry. And this entire thing has its length L. So we need to add this portion to it that we're not measuring from. Oh, or in this case, what we're doing is we're subtracting it from this entire length. We're calling this x. And we're going to subtract this distance because it's already known. We only care about this one. Now, then we're going to add p times this x distance to this cut. And we're going to set that equal to 0. Rearranging, we get our moment is negative q times x minus L over 2 minus px. Now, with those in mind, we're going to come back over here to our problem. We're going to remember our deformation equation. It's going to be the partial derivative of this strain energy with respect to, this time, the imaginary force. Why are we doing it with respect to the imaginary force? Well, because it makes the math a little easier, and because we have to take care of this fictitious force and not forget that it's doing this. Remember, this fictitious force is going to have a magnitude of 0, right? So let's first start off by remembering a process from up here, how we're going to have our partial derivative. Our math is going to separate out into this deformation equation where we're going to have m over EI times the partial derivative of m with respect to the fictitious force in this case. So let's start by finding our partial derivatives with respect to the fictitious force as we've done here. Now the partial derivative of this with respect to q is 0 because we're treating this as a constant, so the partial derivative is 0. Now the partial derivative of this m with respect to q is going to be negative x minus L over 2, right? Because this doesn't have any q terms, so it's treated as a constant and 0, and we're treating like a normal derivative there, so we just pull this constant out. Now, in this case, we've kind of made it simple, and we've combined these two equations into one bigger equation, right? But it's still the same process. We're going to integrate, or plug in and integrate. So basically this one is going to be m1 over EI, with the integral from 0 to L over 2 of m1 over EI times the partial derivative of m1 with respect to q dx, plus the integral from L over 2, so this next part, of m2 over EI with the partial derivative times the partial derivative of m2 over partial with q times dx, right? We're going to set this equal to 0 because our partial with respect to q is 0, making this whole side 0. So then we're just left with this part. This part is going to boil down after we start to plug everything in. We're going to have our m equal to, sorry, we kind of got jumped a step ahead here. We're going to plug our m2, which is this equation, into here over the EI, and we're going to plug this dm over dx into here. Simplifying a little bit, we're going to end up with the integral of L over 2 to L of px over EI times x minus L over 2 dx. Now when we integrate that, we're going to end up with PL cubed over EI times 5 over 48. That's our final answer. See, to do this, we couldn't have solved this problem without this fictitious force. And this fictitious force comes in real handy to help us negotiate certain problems where we otherwise would be unsolvable without it. Now, let's kind of take a look at it. Let's take a step back real quick and wonder, what if we have a moment applied at the end instead of a force? Well, the process is simple and it works in a similar way. There's just one problem. What are we going to use to differentiate with the partial in our partial derivative? Well, as we've seen before, we're taking our partial derivative of our strain energy with respect to our force, right? Well, here, we're going to have to take our partial derivative with respect to the moment, because that's what we've been applied it with, right? So, as we do that, we see that we could apply the equation in a similar manner. So applying it in a similar manner, we just have this problem here. So we're basically going to ask to find the deformation of that beam at the end, but this time with an applied moment instead of an applied force. So here, since we don't have a force, let's apply a fictitious force again. Let's apply this here at the end and call it Q. And remember, Q's magnitude is 0. Now, let's draw a free body diagram. So here's our free body diagram. We're going to have our moment that's being applied, our fictitious force, and our moment that's being caused. And we're measuring from the right side in. So let's sum the moments. Summing the moments will give us m plus this initial moment plus this q times the distance x. Rearranging, we get m equals negative m naught minus qx. All right, so in this case, let's look at this. In this case, our theta, we're defining theta as our deformation, is we're looking for a deformation angle, which is why we're given it when we're doing moments, and we're taking the partial derivative with respect to a moment instead of the force. We're going to be given an angle instead of a distance in deformation, which it's very similar. You basically just do this and you're finding an angle instead of a force. So that being said, let's apply it to our normal force and find a distance, right? So applying it the same way, we're going to have our integral of m over ei times the partial of m with respect to this fictitious force q times dx. So that's going to, plugging everything in, we're going to have the integral from 0 to L times minus m over ei times x minus dx, right? So doing all the math, plugging everything in, we're going to boil it down to m naught over 2ei L times L squared. That's our deformation equation. Now let's apply it with this instead of our deformation equation that we've been doing before. Our angle of deflection is working the same way, is the integral from 0 to L of m over ei, this time with the partial derivative of this moment with respect to this initial moment times dx, right? So plugging everything in, we're going to have the integral from 0 to L minus m naught over ei times negative 1 dx. Doing the math, doing the calculus, we're going to end up with our deformation angle equation of m naught over ei times L. Why is that important? Because not every problem is going to have a force applied to it. And you need to know that when there's a moment applied, you have to have your fictitious force in there to help you solve the problem to get you your deformation. Because if we just try to work it with this moment, we'd only be able to find an angle. Now, let's combine several different things more. One more thing that we've got is deformation of curved beams, right? This is going to apply most of our stuff and a couple new things too. So we're going to jump back up here again and grab some of the information that we've had before to apply it to this problem. But to apply stuff to curved beams, we have to take into consideration this curved part. We can't just apply things linearly because it just makes things more complicated, and there's other factors too. To make our life simple, let's remember that this curved section, if eccentricity is small, say r over h, or radius over height, like a thickness say, is greater than 10, then we should apply these strain energy, then our strain energy can be approximated with regular energy equations with one substitution. Our dx that we've been using as our integral is going to be switched to rd theta because we're switching into polar coordinates or radial coordinates, right? So other than that, our process is going to be identical, but we have to remember when we're switching to this, we have to include this last r. Otherwise our math is going to be thrown way off and we're not going to get our right answers. So let's see this. Let's look at this example. We want to find our deformation at this point D, given point P, or given force P is applied at C, and other parameters L and the radius of the circle R. what do we have to do? Well, first, like these, let's break it up into different parts. Let's start from the right to left again and label our parts 1, 2, and 3. So we're going to have 3 parts, 3 moment equations, and 3 things to add up later on. So let's look at our first part. Our first part, let's sum our moments. Our moments, we're going to get a moment here, which is our m1, times this force, times r minus r cosine theta. How did we get that? Well, we got that by having this r, which is our radius, minus this r cosine theta here. Because we want this parallel distance, or perpendicular distance, from this line of action of this force to where our moment's being applied. And to get that distance, it's r minus r cosine theta times this applied force q. Rearranging, we get our moment equation is negative qr times 1 minus cosine theta. Now let's move on to our second one and hold that one in mind. Applying it here, we're going to continue this down and cut our section in here in the second part. What are we doing there? So we got our moment 2, our second applied moment, plus PR sine theta. So that's coming from our applied force and our angle theta. Let's call it an angle theta here. Theta. Right? Sine theta. That'll give us our perpendicular distance to the force. Plus QR plus r sine theta. Here it's a similar process here, except for flipping it to sine instead of cosine to get this matching angle. And we're adding r instead of subtracting because we already have this radius. Rearranging, we'll get m2 equals negative PR sine theta minus QR times 1 plus sine theta. Let's do it for the third part. Right, so this time we're going to be in here on the straight path, so we can maybe think about using something linear. So let's cut it again, do our moment, and our moment's sum of moments is going to be m3 times p times x plus r, x plus this radius to get to this p, plus q times 2r, so twice this radius, plus the x, the distance of the cut. That'll give us our stuff. Rearranging, we'll get m3 equals negative p times x plus r minus q times 2r plus x, right? Now let's plug it into our equations, right? So we're going to get here. Remember, our deformation equation is the partial with respect to the strain energy with respect to this fictitious force. Whenever we apply the fictitious force, we always got to take the partial with respect to that. So our strain energy, remember, is going to be the integral of m squared over 2ei dx. Now in this case, since we have the multiple parts, it'll be easier if we sum up the individual parts, applying this equation 3 times to get to our final deformation. So it's basically going to be like this, and to find our normal deformation. So let's start with the deformation from part 1. So we're going to plug our equation in similar to this one again, and we're going to get the integral from 0 to pi over 2, so pi over 2 of m over ei with the part times the partial of m with respect to q r d theta. Remember our r d theta, we can't forget the r or the d theta, right? And we're going to set that equal to 0. Now our partial with respect to q we have that, but our moment is going to be 0. So we just neglect this term. So it's going to be 0. Now let's go to our second part. So we're going to do this again. 0 to pi over 2, so 0 to pi over 2. Plugging this in, so it'll be basically this PR sine theta, which is our n over ei. Remember, our q is 0, so we're taking that out, and basically we can neglect this term and that, so our q is 0. So that's why this term is 0, it's because our q is 0. Now, we're going to do the same thing here. Like I said, we're applying our stuff here, and we're taking our partial of this with respect to q, which will just give us this r plus 1 sine theta, r times 1 plus sine theta, times r d theta. Rearranging and pulling out some constants, we'll have PR cubed over ei times the integral from 0 to pi over 2 of sine theta times 1 plus sine theta d theta. Now, integrating that with our boundaries, we'll end up with PR cubed over ei times 1 plus pi over 4. Now let's do it again for the third one. It'll be the integral from 0 to L of 1 over ei times the moment. Remember, q is 0, so it'll be just this part times the partial of that with respect to the moment, with respect to this q, which will just be this 2r plus x. Rearranging and pulling out some constants, we'll end up with P over EI times the integral from 0 to L of x cubed plus 3rx plus 2r squared dx. Plugging in our bounds, we'll end up with P over EI of 1/3 L cubed plus 3r over 2 L squared plus 2r squared L. Now how do we get to our final deformation? Remember this equation? We're going to apply everything in here together and add them up. Remember, this one is 0, our SD1 is 0, so we can neglect it. Our SD2 is PR cubed over EI times 1 plus pi over 4, and our SD3, our delta D3 is P over EI times 1/3 L cubed, yada, yada, yada. Let's add them up together, and we'll end up with this. Our total deformation equation is going to be PR cubed over EI times 1 plus pi over 4 plus P over EI times 1/3 L cubed plus 3r over 2 L squared plus 2r squared over times L. Now, let's see. That looks like it's going to be everything on here. Now, hopefully I've been able to prove to you that using Castigliano's theorem and energy methods was a more efficient and time-sensitive way of solving these problems as opposed to going through it derivative by derivative and integral by integral. Thank you.